Hi everybody, this is the recorded version of the GC surgery session 4 about GC uncertainty. I'm going to talk about uncertainty concept, and I'm going to try to handle this from slightly different perspective. So I'm actually have the same height as Michael Jordan. So for those of you who knows me, that's probably not really the true fact. This is actually how I look like in comparison to Michael Jordan. But the reason why I dare to say that my height is similar to Michael Jordan height is because we both have the same height of 175 centimeters, but plus minus 25 centimeters. So when we talk about the uncertainty, we have the uncertainty of plus minus 25 centimeters in this particular case. So both of us have the height of 175 centimeters. It doesn't really matter on day-to-day life, but it might probably matter for the NBA. If they want to hire me, they'll probably see that I'm slightly lower than 2 meters, so therefore they wouldn't accept me in the NBA. But it's pretty much all about perspective when we talk about uncertainty. So let's say we go to a restaurant and pay for food that costs us 10 pounds, and normally we give them a tip. And a lot of times we give them a tip between 10% and to 20%. For us, it doesn't really matter giving a tip 10% or 20% because it's only worth 1 pound or 2 pounds here and there. So it doesn't impact our financial health by giving a tip of 10% to 20% to other people. But then if we see it on another point of perspective, when let's say we go on an airplane, we don't probably want to go on an airplane that have 0.1% probability of crash. The only reason why we go on an airplane is because the probability of crash is really low, and therefore most likely we'll get to where we intended to be by taking an airplane. So for instance, I'm not going to take an airplane if the probability of crash is 1 every 1,000 airplane, for instance. So what about gas measurement? For instance, when my GC is measuring CV that is around 40 megajoules per centimeter cube, let's say plus minus 0.3% of measurement, it means that I'm certain that my GC is measuring 40 megajoules per centimeter cube plus minus 0.3%. So what this means is that if we are flowing 1 million pounds per day of gas, 0.3%, it means that on a daily basis, it can actually, we might be losing 3,000 pounds per day, or we might actually be gaining 3,000 pounds per day, but we go in the range of the 3,000 pounds per day. So in terms of the gas measurement, I would rather have a stake of a certainty of plus minus 0.1% rather than 0.3%, because when 1 million pound is at stake, 0.1% means 1,000 pounds a day rather than 3,000 pounds a day. And in a bigger scale of scheme, it's actually a lot more significant in terms of the absolute value of the money that we might be losing or gaining. So at the end of the day, we all just want a fair measurement. So we talk about 0.1% uncertainty of the GC because GC is actually capable of performing around 0.1%, 0.12% in most of the GC that I've seen so far. But a lot of times people actually put in their uncertainty budget of a CV measurement of 0.3%. And it's actually a lot higher uncertainty expectation than the GC is actually capable of. So when we see the GC uncertainty, we can actually see that there are around 4 sources of uncertainty in terms of the measurement. We got calibration guess uncertainty, we got reproducibility uncertainty that comes from daily calibration or validation, and then we got the calculation standard uncertainty, and also we got the repeatability and linearity uncertainty that we can determine from the ISO 10723. Now, this session 4 GC surgery will be split into 2 sessions. So the first one is going to be talking about calibration gas uncertainty and reproducibility. And the second one, we'll talk about the calculation stand uncertainty as well as the repeatability and linearity. First of all, the calibration gas uncertainty. We're going to talk about this because the calibration gas is a really important part of the GC measurement. And a lot of time people don't really understand what is the impact of having a poor quality of a calibration gas. Now let's have a look at a typical calibration gas. This is actually the calibration gas that I have in my workshop here. We can actually see that we have a certain mole percentage, which is a standard component, and also we have an absolute uncertainty of each individual component in there. We can then convert that absolute uncertainty into a relative uncertainty for each individual component. As you can actually see, the relative uncertainty of each individual component here are really low. Most of them is much lower than 1%. We do have quite a high uncertainty for hexane and heptane, but because they are quite a low concentration component, it will have quite a low sensitivity in terms of calculation for the CV. So what does it mean in terms of the actual composition of the gas, whether we actually have that exact composition? What it means is can be shown in the following chart. So if we see just into the methane alone, methane mole percentage and the uncertainty of the methane, we can then have a look at the methane composition of 84.994 plus minus 0.03. So with a 95% confident, we know that the value will fall in within this particular limit. So in an actual case, the methane can fall in there, it might fall in there, or it might fall in bang on right in the middle. It might be right on the limit. And also, because we only have 95% confident of the value that falls in within that limit, there's a possibility that it's actually go out with this particular limit. What does it mean in terms of CV? It means that we can get lucky that we bang on in the middle, or we can get unlucky and we can get somewhere like at the very limit of our uncertainty. So when we have quite a low uncertainty, we basically have a CV variation, the possibility of the CV that is quite low. In this particular case, with that particular relative uncertainty that we have here, we got a plus minus variation of 0.03%. However, if we actually order a cal gas that have 2% uncertainty on each individual component rather than a small uncertainty on each individual component, we will be subject to a possibility of CV that goes plus minus 0.22%. Now this is a problem because the calibration gas quality impact the measurement directly, because our measurement will only be as good as our calibration gas to begin with. So what it means with a 0.22% uncertainty is that before we actually measure the process gas, we have an uncertainty that is quite high already. So our minimum uncertainty to begin with is 0.22%. Now, a lot of pipeline actually say that the maximum CV uncertainty that's allowed for a GC to measure is plus minus 0.2%. But regardless of this requirement, many operators are still actually order the calibration gas that has a relative uncertainty of 2%, and they get away with it. Now, the reason why they get away with it is because this kind of calculation isn't done. If this kind of calculation is done, that calibration should have never been installed in any of the installation. So at least what we recommend, at least to have a calibration gas that is less than 1% uncertainty on each individual component. So therefore, you have quite a reasonable low uncertainty when we start measuring the actual process gas. So the second source of uncertainty is the uncertainty from reproducibility. So what we're doing here, we basically take a daily calibration result, we create a control chart, and we see a natural variation of the GC, which is measuring, pretty much measuring the calibration gas in the form of calibration or validation. So we're gonna put an example of a response factor trend that looks like this, and we're just putting 12 data here just for ease of the demonstration. Now, also, this is a hypothetical number. It's not really coming from an actual GC, but I just want to prove a point here where when we get a variation of response factor in one component and every other component goes with the same exact variation with everything else, it basically means that it doesn't have any variation at all, because at the end of the day, when we normalize it, everything will go back to where it should be. So in this particular example, we have a response factor to begin with. We got it at 0%. So this is the actual response factor that we use as a footprint. So this is the basis of the comparison of any other data that happens after that particular point. So if you can actually see that the first point here, there's a 8% variation from the original response factor, around 8 point something variation there. And then it goes to like up and down in quite erratic manner. So you thought naturally that something's not right with this GC because there's so high of a variation in the response factor. So what we want to do here is to show that it's not really actually the case. And by doing that as well, while doing it, we want to demonstrate how we can actually calculate the uncertainty of this particular GC from this 12 particular data point, basically. So if we go back to the basic, response factor is peak area divided by the calibration gas mole percent. So what we can do then, each individual response factor that you see here can then be converted back into a peak area. So the way we convert this response factor individually by taking the response factor and multiply that by the calibration gas mole percent, which we already know. So by doing that, we can then convert each individual response factor data on this individual points into a peak area data. So what we do is basically we take all the response factor and convert it into peak area data. And this is the peak area data that you see. I know this is like a number at the moment, but it will make sense because I'm going to put them into charts later on. We basically do then from there, from the peak area information, we then convert this data into mole percent. But the way we do it is by using the footprint response factor as the basis of conversion to the mole percent reproducibility. So what we're doing is basically we're almost like treating our footprint as our calibration response factor, and we basically almost like performing a reproducibility test by entering the calibration gas as an unknown and look at the actual mole composition if we put that calibration gas as an unknown and use the response factor from the footprint. So what we're doing is we basically take the peak area from each of these individual points and then we divide it by the footprint response factor. So therefore, each individual point here will be converted into mole composition using the response factor that comes from this footprint here. So it truly is just a reproducibility test. It's almost like when you're doing a repeatability test, but a lot of times you're doing repeatability tests by running 5 runs. So what we're doing here, we're running reproducibility tests using the calibration data, but with a lot more runs than just 5 runs. And then we basically look into the reproducibility of the actual GC measurement by analyzing the calibration gas in the form of calibration. So what we do here basically in the table, we take the calibration peak area and divide that or multiply that by the footprint. And what we get, calibration peak area, divide that by the footprint, and what we get is the reproducibility mole percent. So when you see that naturally the peak area goes all over the place because the peak area is to do with the variation of the response factor. If the response factor goes up by 8%, that means the peak area will go up by 8%. So when we convert that into mole composition, you can actually see the reproducibility mole percent doesn't look reproducible at all. You can actually see that it varies from 84.9977 to 91, 89, it goes all over the place. But what we're saying here, this is actually an unnormalized total, unnormalized reproducibility mole percent. So if I just bring your attention to just this particular data, the first calibration data, we got this data for methane, but if we expand it to every single other composition, we can then see a normalized total composition that looks like the first column. So we got a normalized mole percent for methane, we got a normalized mole percent for nitrogen and every other components. When we sum them up together, we got a total of 108.2%. Now this is very consistent with the variation of the response factor just now. As you can see in the initial chart, we actually had an increase of response factor that goes up around 8%. It actually went up by 8.2%. So it's represented by the unnormalized total here. What happened then is we can then normalize the data, and when you see the normalized data to 100%, then it becomes very, very comparable in comparison to the calibration gas mole percent. In fact, when you see the difference between the normalized mole percent and the calibration gas mole percent, you hardly see any difference. So we got this for every single run. We got this for the first run, for the second run. So the result for the second run, you can actually see that the difference is also very, very small, and it's really consistent for every single run that we have. Now if we go back to methane data alone, we can actually see now that methane variation with that same logic goes up and down from 84.9977, goes down to 84.997737, up and down, and you can actually see the two standard deviation of all this data, the 12 sets of data, is 0.0000034. And this is the absolute uncertainty. Now I know with the 12 data, we should actually get the student t statistic, but this is just a concept that I'm talking now, because when we actually have the actual GC measurement, we will have a lot more data rather than just the 12 data. The 12 data here I'm using just to as an ease for demonstration, but in the actual case we'll have more than 30 data. In a lot of cases we get more than 100 data, so that we get an actual representation of what the uncertainty of the GC is. So from this two standard deviation of which absolute uncertainty, we can then convert it to a relative uncertainty by dividing it with the actual calibration gas mole percent. So from here we get plus minus 0.000004% of the uncertainty of the methane. Now, the only reason why we get such a small number here is because the variation on the response factor of methane is exactly or very, very similar to the variation of the response factor of everything else. If we basically see the overall uncertainty, you can actually see the uncertainty of methane, nitrogen, CO2, and every single other gases, and all of them have a very, very small uncertainty. And this is, again, because the variation of each of the response factor is matching between every single gases. Now that's why we have this particular small uncertainty. Go back, this is the error, overall response factor error trend that we have, and it goes up and down by 8%, plus minus 10% here and there. But because everything goes up and down in a similar manner, we can then actually say that the uncertainty of the measurement is really low with this particular response factor trend. Now, to reiterate the importance for having a control chart, not individually, but having them all together in the same chart, is really important for the GC for this particular reason. Because when you have a variation of the response factor in methane, let's say it goes up by 5%, it doesn't necessarily mean that the GC is unhealthy. But we really need to have a look at it in quite an overall manner rather than look at it individually. Now we can actually use this information to determine the performance of the GC longer term. And we're going to talk about the uncertainty trend as well on the second session of this particular uncertainty session. I'm going to show you a case where we have a natural variation of the response factor that comes from the actual GC. So this is going to be shown in the software called GCAS, and this is pretty much a conditional-based monitoring tool software to analyze the health of the GC. So we got this demo A, and I'm just going to show you what it looks like. So to begin with, we start with the data analysis. I'm going to get the actual trend where there is a data in there. So this is how the methane response factor looks like, and if we plot everything together, we can see that everything goes up and down in a quite similar manner, but we can see that hexane is performing slightly worse than every other components, and we can also see that heptane here is performing slightly worse, although it's not as bad as hexane. So visually we can tell that the GC is actually healthy, apart from hexane that has slightly higher variation, and also heptane that has a slightly higher variation. So we can then basically quantify this chart into an uncertainty statement by combining all this particular data and do the uncertainty calculation as shown previously. So we got to the uncertainty calculation. As seen before, there is 4 sources of uncertainty. So for this demonstration, I'm just going to take the uncertainty from GC reproducibility because that's the only one that changes, and that's what we're interested in at the moment. So we basically select the calibration gas certificate. So this is the calibration gas certificate that we have, which is the data that you've seen before as well. So this particular calibration gas that we use is going to be used to calculate the reproducibility mole composition. And then we select the data range, and this is pretty much the data range that we see in that particular trend that we have just now. And then from there, we can actually see the actual calculation of the uncertainty of the reproducibility. And this is almost step by step of what we show you just now in the presentation on how to calculate this mole composition and how we then come out with the 2 standard deviation of it. So we get the response factor of the footprint, and then we get the footprint peak area as well. And then here you see the calibration response factor as an average value. But then if you click on it, you can actually see each individual response factor and the peak area of the data. You can basically copy all this, just block them all, and copy that to Excel if you want to do your own analysis. But then it also gives you a detail on what is the standard deviation, what is the average plus minus 2 standard deviation of it, and also the information on the peak area. So from here you can get the calibration peak area as an average, and then convert that peak area, divide this by the mole percent, divide this by the footprint response factor. Then what you get is the unnormalized composition. So this is the average of the unnormalized composition that we're using here. And then we can then normalize it, then you get a normalized average composition or measured calibration gas composition that we have. So from here then we go further, we get the standard deviation of the measurement, and we then have the average plus minus 2 standard deviation of the measurement. So you can see the 2 standard deviation is 0.013%, and the relative uncertainty of that particular 2 standard deviation is 0.008. Now if you notice on the top here, you can see that k equal 1. This means it's just 1 standard deviation. So you basically divide this by 2, and then we get the relative uncertainty from the actual component of the gas. So if we talk about two standard deviation, this will be 0.016% on the methane, and this will be around 0.08% on the nitrogen. So we then from here we can actually see the summary of the uncertainty. You can see the methane uncertainty is 0.16%. And nitrogen uncertainty is 0.08%, and you can see every single gas's uncertainty in this particular summary page. Now, based on the trend before, we noticed that the heptane and hexane response factor is slightly more unstable in comparison to everything else, and this can actually be seen in terms of uncertainty number. You can see the uncertainty of hexane is higher than everything else quite significantly, and heptane uncertainty is higher than everything else, although it's not that significant, as significant as hexane. But we notice this as well in the chart qualitatively, that heptane is slightly higher than everything else, and now we can quantify this as part of heptane uncertainty. Now from this we got individual calculation of the uncertainty of the gas, so we can then after that convert that into the uncertainty of, let's say, calorific value or any calculation standard uncertainty. So what we do is basically we feed in the information of the calibration gas composition into the calculation standard, and then from there we can then calculate the sensitivity. Now the sensitivity calculation will be a subject for the next session of the GC surgery. So basically, just to summarize what it is all about, is that each individual gas will have a different sensitivity towards the actual measurement. Let's say a gas that have only 0.1% of a composition will not impact as much as a gas that have 80% of composition. So 10% of a change in heptane composition or variation in heptane composition will not have the same impact as 10% variation on the methane composition. So from here we can then calculate the sensitivity of each component, and then therefore we can calculate the overall uncertainty that each of the component have in terms of calculation standards. So we basically can come out with the uncertainty of the CV, standard density, line density, velocity of sound, any calculation standard that have gas composition as their input, we can calculate their uncertainty. But then we're going to talk about it on the next GC surgery session. So in terms of the paper, if you want to take a look at the paper, you can actually download the paper from www.i-Vigilant.co.uk/download. You go into the publication section and you can get the data or the paper. The Southeast Asia Workshop 2014 talks in detail about the uncertainty method that we're doing. And if you do have any question, you can actually pose the question in our LinkedIn group, or feel free to send me an email, for Raybone, an email, and we will try our best to answer your particular question. And this is pretty much the GC surgery session for the first section of the session 4. I look forward to seeing you on the next one. Thank you.